Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have lecture 5, and the title of the lecture is Parallel Algorithms and Data Structures. And it builds on the previous lectures, understanding a little bit more about parallelization methods, domain decomposition, and also, of course, the, let's say, de facto standard for doing communication in large-scale HPC systems using MPI. But before we dive into the material of lecture 5, let us review shortly what we had the last time. And we talked about in lecture 4 mostly about simple but interesting, powerful techniques in MPI that advanced a little bit the view that we had before from MPI. We started in lecture 2 quite simple of saying there's a point-to-point communication, the send and receive. We had the idea of a ping-pong application as an example. But then we elaborated a little bit and said that cannot be everything what MPI has to offer. So we looked into collective operations, broadcast, scatter, gather, and so forth. And we found that this is already quite powerful. So I can scale with this up very much to an interesting number of cores that I otherwise would, basically do manual programming with, like send and receive with 1,000 processors, which is infeasible. But then we also learned that this is just basically the first part of MPI. And by now, I think everybody of you in the assignment will already be advanced and has already started using this material, and better understanding hopefully is gathered by you by using all these operations on a real HPC system. However, looking on MPI, of course, there's much more to it than our initial lectures reveal. And based on the domain decomposition part that we learned the last time, combined with this, we have now here much more interesting aspects that we want to look at. And the first is really thinking about the MPI communications in more detail, think about differentiating between compute, networking, and storage. And we started a little bit the last time really by understanding that MPI has not only this blocking communication that you already know. So for every MPI send, basically, I need to have a matching MPI receive. And when this is sent, nothing happens. So I really have to wait automatically with this blocking operation until there's somewhere someone who is initiating an MPI receive. And this can lead to performance bottlenecks, as you suggest here, right? Here's a processor already waiting for the receive while nothing happens. And we look more in these phenomena when we come to performance analysis in detail. But then we learned also that there are so-called non-blocking operations in MPI, MPI I receive and MPI I send, where you basically then can have different, let's say, communications realized where you already receive here, but can do other things. And then you have that kind of MPI wait statement in order to receive some element from the other processor. And there were many aspects to it. We have an MPI I send, it can work with the MPI send here. In this example, it doesn't matter. But non-blocking communication, of course, can be incredibly important to really get more done. But of course, on the other hand, enables you also to create more performance bottlenecks. So it's really something where performance analysis tools then in one of the upcoming lectures will help us to understand this phenomena much more. So obviously, this is just, let's say, very theoretical in this lecture. We already learned that basically the practicals, which I will bring in practical lecture 5.1, will give you some demonstrations on that. And of course, then one of your assignments will also go into more detail. Another powerful aspect of communications in MPI is the world of communicators. You learned already MPI com world is basically the world of all the communicators. But we also learned that this is not everything. You can create subgroups that then basically, based on these ranks on MPI.com world, will be basically assigned to another communicator. Let it here be a row-wise one, where we have this color encoding, assigning rows as just one example, where basically each of those processes involved gets another rank. And this is important. So you still maintain the other rank in the MPI.com world overall communicator, while in the new subsequent created one, you assume a new rank. Basically, that means one MPI process has different ranks in different communicators. And of course, you can create another group with a complete different setup. You learned about the very powerful Cartesian communicator, assuming more or less a Cartesian grid structure that we had also with the ocean is often, explained, but could be, of course, any domain that you want to simulate. And then you can use this collective operations with all of these. You can do, of course, still send and receive by the individual ranks, addressing then this particular communicator that you choose for. And this is quite a powerful method. So you can implement very different communication aspects really on top of each other, so to speak, by involving always the same MPI processors, but for different elements, right? So this is a quite powerful phenomena. But we also learned that even though we want to scale up, which is, basically one of our key considerations, if you remember lecture 3 a little bit, why we do all this, we want to speed up, we want to increase the number of cores and then being faster done, or enable basically applications or parallel applications where, memory is the most crucial thing. You need just more aggregated memory across different nodes in order to, simulate a problem. And here we learned some limits and some impacts in the networking design. You see here one of the examples of having dedicated I/O nodes in one of the HPC machines, while all of them do computing. There's some nodes that really have then the really I/O link to the real storage systems. So naturally, if I increase my scaling to more and more cores and have more and more computing done, you see that the I/O nodes will here and there probably show some limits or some congestion really on the network in some, respect, because they all have to drop it to disk and it goes always through many different I/O nodes, but the compute nodes are usually much more. So essentially, we talk about this kind of small bottleneck here, where many compute nodes have to go between different I/O nodes and then via a switch to this data storage, file service, and so on. And this already alluding us to the next big topic in MPI, how to deal with such problems. Of course, when the network fabric, we talked about InfiniBand switches, if you remember the last time, and this is basically, of course, a physical bottleneck. What we do more when we think about here in parallelism on file systems level and storage. So we immediately come to the point that when we have many processors that can actually write data and generate data and all this computing, basically can pile up a lot of basically output for storage. And with this, the question remains how I actually store all of this when I have a parallel program. The same is actually true for open, shared memory processors and things like that, but we will come to this in later lectures. But we also have learned in the last lecture that basically there are different ways how you could do it. You could think about this phenomena where basically you have a parallel program and one processor is, responsible, or one process really here from MPI is responsible for performing the I/O. But this also has some limits and of course, perhaps some overcommitments of this process 5, because then it essentially has to digest all essentially data coming first from all the other processes in order to perform some disk operation, while the others may have to wait until the results are stored to continue the operation. Then on the other hand of the scale, you would think, okay, when we have so many local operations and they are very active, communicating with each other, all these processors, you can have a kind of process local I/O. So everybody creates a file. And of course, immediately here we realized that the file system limitations kick in. So the more files you generate, which might be totally fine if you create 5 files here, but you think about that we are interested in scaling up, speed up. So we do this for 1,024 processes, for 2048, et cetera, reaching to 10,000 and more MPI processes. And with this, a file system is actually quite busy of creating inodes and metadata for different files that are all created almost at once. Basically, when there's a checkpoint maybe for I/O in the I/O strategy of the particular application. So in other words, this has also scalability limits, and we will observe this when you basically go to really using a complete HPC systems with 500,000 cores plus or so very easily, that this is not really a scalable solution either. So what people then have thought about and basically come to one of the standards of MPI is then this kind of parallel and scalable I/O using so-called basically MPI I/O methods. And we will also explore this much more in our assignments, and I can present basically in the last lecture. But here the idea is that you have a binary file somewhere and you assign different parts of it, enabling also concurrent access to this file. So this needs really a parallel file system that is there in order to support the concurrent access to one file, which we learned is essentially, of course, not in the end really one file. It's a logical file, not really existing on the different hard disks or IO nodes, but still captures the essence that for the application programmer, everything can be written in one single logical file. And then with basically we learn striping and so on factors, you can really move it to real storage systems. And that's where we left off. So definitively we have seen that MPI is very powerful in different communication schemes, is blocking, non-blocking communication. It has very powerful communicators to basically design the communication. It has certain limits in networking we always have to be aware of, especially if you scale up to many, many cores. And then basically we have seen that in order to deal with this big data that you basically create the large storage requirements, there's only basically this file system or parallel IO method that is really then so-called the standardized methods how to do parallel IO here and basically in HPC. That's what we learned the last time, but it's time to go ahead. So here we have a more practical topic lecture showing you some examples of parallel algorithms and data structures that we will also have here and there in assignments. So basically starting a little bit with very simple parallel algorithms up to some very complicated algorithms like the fast Fourier transform, which actually then shows you that not every time you have to implement MPI from scratch. There are lots of libraries available that already basically leverage the MPI standard and that you can use them with your communicators and with the application domain problem at hand. We learned a little bit about non-blocking communication and simulation sciences. So why can that be useful? And have, of course, some advanced parallel and scalable algorithm examples. However, here goes the idea, of course, that this is just an appetizer for the second part of the lecture in HPC, right? We said like from lecture 10 on, we will have one application domain after another, where of course we pick up on MPI, we pick up on OpenMP, where we show actually where these things are really used in practice. While here I just give, let's say, smaller examples in the beginning, how rich MPI can be, especially being the de facto standard in HPC for parallel computing. Then, of course, when you dive a little bit deeper and think about what domain decompositions could be possible, we learned about this a little bit in lecture 3 already, so lecture 4 extended here and there. But of course, we always had this more Cartesian idea of the world. We broke the ocean into blocky parts. What are the limits of domain decomposition? We learned about actually halo and ghost layers, so how they actually have an influence and how you do your domain decomposition, and then think about perhaps particle interactions of long range and short range. You would maybe design a different structure, which could be a tree-based structure. Then when you think about MPI and what you do already in your assignment, you have lots of simple basic building blocks, right? Where you think about, we just actually sent an integer over the wire, and then we send a char over the wire. But what about strings? What about a sequence of different data types? Do we do a send and receive all the time and have network overhead over the time for each different integer we want to give over? So here we're talking much more about how we go along with arrays, how we go with multidimensional data sets having different data types, which are derived then from the basically MPI data types we will learn of. And then I show you some illustrative examples leading up to one of the most, let's say, used elements of parallel IO we learned essentially the last time. On top of that, you would employ NetCDF, you would employ hierarchical data format files, which are really, let's say, de facto standards of the community. And we look into this a little bit, how this is used, for instance, in clustering of applications, where I give a data science example. So a very interesting lecture showing you again some connections of, in a way, lecture 2, lecture 3, and lecture 4 combined in lecture 5. And in a way, also just as an appetizer, so that you learn more and more parallel programming is a complex topic. It entails domain knowledge, it entails thinking in parallel, it entails IO problems when you scale up. And of course, the overall idea of always increasing the cores to obtain the speed up, otherwise we wouldn't do it. So with this lecture, you combine different pieces, and then we are ready for some practical elements, which I show you in practical lecture 5.1, where we take all of that, what we learned a little bit in lecture 3, 4, 5 combined, and put it then into some interesting examples for you. So in a way, then after this, you basically are ready for, programming your first baby steps in MPI when you have a real application domain problem. But let us come now to the idea of having a bit more advanced parallel algorithms, of course, still to a moderate degree. The last time we had the maximum of an algorithm that was somehow looking at arrays. Okay, thank you very much. That's not so much a big deal, but let's look to some more advanced applications. And when you really look at them, and we will probably here focus a little bit, of course, on the idea of having distributed memory, right? So that means really message exchanges are necessary. We use the MPI standard here as an example. And then we have interesting applications that you immediately could realize, like this kind of CFD application here of a Formula 1 race car over time simulated. Or you have this heat map that we explained perhaps in the classroom, understanding at what point in time I have actually some certain heat. So the way how you always do this, and we learned this a little bit in lecture 3, I told you there's always this kind of domain decomposition in the beginning. You have to understand the problem a little bit. That means you want to break down perhaps the air and the race car itself, or different parts of the race car. It is always an application domain oriented idea of how to do domain decomposition. Then you start writing manually good MPI code maybe to break that down. But usually it is a challenge to come to the third part where you would say integrate it very well then with the technical code and the problem of the domain codes, which means you have to introduce equations, right? Like in computational fluid dynamics, things like Navier-Stokes equations, airflow. So physics have to be joined then with computer science code, which usually makes it very challenging. And we will look at some examples also basically as part of this lecture when we have this heat map and stencil methods. So it's a very interesting way how to think about a computer science problem here, which is more or less computational engineering, because more and more we have this engineering part of it, of physical formulas, numerical methods based on known physical laws, how you basically enrich then this kind of typical MPI code, you would say, because otherwise we usually don't want to have a parallel application. The physics equations, sometimes PDEs that have to be resolved. We'll come to this in a moment. These are all computational demanding problems, and that's why you want to scale up. You want to employ more processors to really achieve a speed up then. And some of you already, when I hear it from the quick Q&A, actually we're going to these operations, and that's very good that you already experimented with them in your assignment, because this carries much more weight than just putting it here on the slide. We learned about this MPI scatter operation, which takes essentially an array, breaks it into different parts, and then sends it to all the ones that are in the communicator, right? Again, it's a collective operation, and the receivers here are basically then selected by using an MPI communicator. That could be MPI convert for everyone, or if you basically derive a kind of subcommunicator. Also, we learned we have to have this sort of interesting buffer to be basically ready for sending. And then on the other hand, of course, for those that are not basically are the sender, we want to be ready for receive. And in order to have this space free in C, we really have to prepare for that. And when we now want to think about how this could be used in a practical application, let's assume a very, very simple one where we have here essentially just a typical add operation of two different distinct vectors here in order to come to the Z vector here, where we can maybe use scatter and then also gather again. So the other one, hence, we want to have is we want to scatter first the array, we want to do something with it, and then basically gather again the results. Of course, this is in this particular example, really, of course, a very simple example. That's why I want to basically give you this as a very first example, but still it carries the essence of these operations, while of course much more is possible. And here we have the so more or less inverse of MPI scatter, of thinking about that here we want to get the data from different processors in order to get the update of the array at the one processor. But all of course, is also then derived on the particular MPI communicator you choose, and basically then think of the rank that is then really the receiving one that gets essentially all this array filled. And hopefully this will be with results, of course. So with this application problem, let's go to some source code, which by now hopefully means a lot to you from the basics. I mean, including MPI should be part of your assignment. MPI com rank, MPI com size should be now known by you by heart, especially MPI init and MPI finalized, what you always have to do to have an MPI environment. What's new is now to think about how we could implement such a thing by using scatter and gather. And of course, here you could think that the color codes already says it all, right? So basically, in order to do this mathematical equation, which admittedly is very simple, you just follow the color codes in order to have this. On the other hand, it shows you how nicely parallel this is. You don't need for the red to compute any information of the orange or the green cells. So here we have the idea of cutting that, of course, then in different chunks, in basically not only on this level, which is perhaps, if you want, the X part, I called that, and Y part. Also, of course, then the kinds of chunks we have from this different, times of doing this in the different rows here. And immediately you think like we defined it here, of course, for 3, but there's not basically a limit. You could, of course, go deeper and deeper. And the more cores you have, you can easily parallelize this more. And this gives you then the idea of doing this basically per chunk here, where the Z part, of course, for each of the individual parallelization schemes is like the X part and the Y part added together. That's what we know from the color coding. And basically then I can actually use scatter to get this information out to all the different processes of the X part and the Y part, while then essentially all of them independently just compute basically these parts, the Z part. But of course, then we also basically have to gather the whole result of the Z, because basically everybody has now a certain, or basically all these processes have now a certain element of Z, but only a Z part of it, of the whole story. So basically the gather now enables that one of the processor we determined as a root has then the whole picture computed in parallel. So a very simple code, but in a way very powerful, because if you think about the lines of codes, you don't have to do very much. And in order to really, this does this in parallel. And of course it's scalable, quite some fraction here in order to enable much more processors that I can then determine via the job script. So let us move to then something we would call maybe a nice idea of, have this a little bit more, let's say, as a shortcut. We have seen the reduce operation, where instead of you've seen basically going through a iteration over a loop in order to get then, the scatter and gather results, and basically you basically have the MPI reduce operation where you can have the global sum directly involved as one example. And of course, you can also use it in a constellation like this. I increase here the complexity a little bit, but really just a little bit by having the matrix multiplication with a vector. This will be interesting for us because we pick on this also later in GPUs again and deep learning. But still here, think about MPI again, has a very nice idea in parallel computing here of just using the color codes. Again, you see we can nicely put that into different parts, because all the color codes here show you what is the dependency, and everything else can be nicely independently computed. And this is something where we look in this patterns for parallel computing in order to achieve basically then the speed up. So here's another view on this, where you think about some pseudo simplified demo code. Here and there, I leave some elements out that by now you really know, like preparing the MPI environment, MPI init, perhaps an initialization of the matrix is necessary with some values we're interested in. But much more importantly here in this course, of course, is your thinking of going parallel. Hence, we think about much more MPI processes here. So if you want, you see here the result array A, and then basically the different domain decomposition in a way of this matrix vector multiplication. You see that basically for this, we have always this B part multiplied by this C part, and then we go back, then have the other processor, have another C part and the yellow part computed. And the color code essentially says it all, how this can be nicely independently computed by 4 processors instead of one processor that has to compute this one after another. And with this, you should be having at least theoretically a speed up. Of course, for such simple problems as a 4x4 matrix, you wouldn't do this, right? Think about that large HPC systems have multidimensional matrices, have a very, very large matrix space, and then, other feature vectors. So here we're talking about much more computing that this simplified scenario, but it captures the essence how that works. So you'd still think about this nicely parallel parts that you really are interested in. So here, basically, we have the matrix then where we perhaps think about a column-wise domain decomposition. That's already what I told you. We have this different parts here initialized, and this is, of course, something which we then are interested to compute now. And I think many of you can already imagine how that, is basically alluding to with the reduce operation, because you see here lots of pluses in all of this, which basically is given by how you would B times C actually compute. But let us go through that a little bit. And again, this will be also shown to you, of course, as a concrete example in the practical lectures. We talk about MPI world rank size. That's what we know. Initialize the matrix a little bit, initialize the vector here a little bit. And then in the next, we already talking about a little bit about a barrier so that we know that all the different, let's say, operations, that's what you also learned in the last lecture, we can synchronize a little bit here, that all the processors have to wait from each other and wait that they are here at the same position. And then you start off really, again, you scatter, right? Of course, to the different, let's say, columns. We said the number of columns matter. And of course, what you also have to scatter then is not only basically this part of the matrix, but also the part of the vector, your C part here from this different color codes. And then on the receiver sides are now the different processors that basically can compute their part. We know how this is actually computed here. There's the different parts in order to get to the A part, which is really just the part from a particular result, right? And that's the important scheme here, where while this is computed, we just have the part of the story in each of the processors. So again, we would need one processor that is so-called the manager in a way, or as we would rather say, the master and worker node, that basically then the master would know the answer. And hence we do here the reduce in the A part, getting essentially here not only all the columns back that we computed, but directly had the sum of all of this inherently by specified then the MPI sum operation, the reduce part. And this is, again, a very conceptual view on this, and probably for some of you a bit theoretical maybe, but still it's a very simple problem, and in a way you understand directly how parallelization and parallel algorithms here help in order to solve that problem and then speeding it up. And again, of course, there are no limits. In a way, you can have much more bitter matrices or also vectors. And then you basically would say, that's what I already discussed here in the previous slide. You put with your MPI reduce the emphasis on the plus, but you don't have to do plus. It could be also something else. Of course, you have to basically come to this, what the mathematical equation or the physics equation will basically command you. So, of course, these were simple problems. Let us come to advanced problems in science where you want to maybe do some signal processing of sorts with pressure values over time. You see here some examples of those more, let's say, periodic phenomena. So you basically have here certain signals with certain frequencies. And basically, to decompose this and have a sequence of values of these different frequencies, you could have something what we call a discrete Fourier transform, which is very, very costly in terms of computing power. It's basically using directly the mathematical formulation, and in practice, it's really often too slow. And O to the n square, which is quite some runtime. So people have invented the fast Fourier transform FFT, which has a logarithmic runtime, much more suitable for computing. And in a way, it's really basically something which you can derive today really from libraries. And it should tell you that basically for those problems where you have a certain amount of, let's say, different applications that would be interested in such, let's say, a study of frequencies. Here, it's maybe an example of a sound frequency unmixing system that you want to really understand. But let's say in many different fields, the use basically of this discrete Fourier transform and then the practical implementation using rather the fast Fourier transform is of incredible value in science and engineering. So people have thought about this many times and actually have created so-called libraries, which we can just use again. You see an example of a Fortran one with the fast Fourier transform in the West versions, where basically these are already, let's say, very optimized for shared and distributed memory. And of course, before you, let's say, potter off and do the mathematical definition and all implementation on yourself with MPI and so forth, the idea is always first, before you have a problem at hand as a parallel algorithm developer, what are libraries that support me in the physics? What are the libraries that are already out there? And I think the FFT is a very important part. And you see here how nicely that can work. You include it, as another library, which is of course based on the MPI library. So you maybe have also to include the MPI library itself. And here you have this fast Fourier transform one in a specific version. So here you have to be careful and remember this needs to match the module load as well. So having maybe this module available that is installed somewhere. And here you have just examples, and it's not necessary that you have this by heart to be understood here. It's a specific distribution that you do here. But more interestingly, you see the MPI com world is again there. So we involve all the processors, but the real scheme of how to do now the different MPI operations is hidden, and you don't have to anymore really deal with it very much, right? So this library takes care of this distribution. All you have to focus on is how you have your domain decomposition, because this in the end is your data, is your input, is your application specific part, what the library then will compute for you. And this is the power then combining MPI with a really, of course, admittedly abstract application example here, which is an amplification factor, because many people use let's say, the fast Fourier transform of different applications. And with this, you have a very good, let's say, way of including this in many different libraries. And we will later learn that in I/O, it's the same way. We have to include the HDF library, for instance, parts which were also in your assignment, in order to get access to parallel I/O and, basically portable file standards, which we're going to use together jointly with MPI, and MPI I/O will support it nicely. Towards the end, basically, let us have another example with broadcast here, where I also want to show you a little bit parallel algorithms really at the cutting edge, perhaps, also based on a, interestingly enough, personal example, but it really captures the essence how much you can use HPC systems in different ways, also enabling quite interesting applications. So here we're talking about an application that employs computational steering. So here we would be perhaps interested, and this is a real life work I did quite some while ago, where I was myself rather in PhD studies. So basically you see here a black hole and different stars around it, and they interact, of course, with different equations of physics, astrophysics example here, what you see in a galaxy forming, and then you perhaps want to understand how this interacts with the different stars, being largely a particle problem using a so-called PEPSI library. Now, the interesting part of this computational steering is now that while this is, of course, in parallel computing with MPI, and you see that a little bit here, of course, we use broadcast and these things, and to understand all of this here is not so important. It's rather an example of showing you how deeply that goes. But the real power of steering is that you essentially not only simulate step by step, you influence as a user. You as a human being essentially change the parameters interactively. And then you compute this in HPC and give the output and visualize it. So what could that mean? You essentially maybe drag the black hole here or basically other parts, which, basically into the stars. And over time, of course, given the equations of physics, it will interact with all the stars. Then the next example we want to have is the data parallelism here, where you have formulas really basically across different domains, right? Using this domain decomposition principle we already learned, and a so-called isotropic lattice technique, where essentially this equation is more or less computed over time in all these different tiles here. But what we also learned the last time basically was, in order to compute this interesting, heat diffusion, or basically more generally diffusion equation here, in order to compute the heat in the room properly based on physics, you actually need from the time step before the data, right? That's what we already learned, and on lecture 7 we will also extend this. And this is a certain procedure we call stencil methods, because in the end, you basically apply the same functionality over here that in parallel. And then, of course, in order to have the right in the next time step, you basically employ then this MPI communication. We also learned here to maybe combine this with the halo and ghost layers. But here you see, let's say, how that can run, and basically have certain elements, how you break down this, domain into different pieces. But by using this, of course, now with a computational demanding problem. And this basically equation has to be, of course, computed over time, right? You see here the different time steps. And at each time steps, it needs to be recomputed because the data is different, right? I get different heat signals, so to speak, when you think about this, after so many rounds from the neighboring processor. So my own computing will be influenced. And this is a typical, basically, data parallel problem. We will also have many application examples later in the lecture. And the people, how they would basically use then blocking and non-blocking communication will be something we will see are also in many different algorithmic examples. Here's one where you basically would think about how you can maybe distribute information with all your different neighbors. And you see here this kind of non-blocking communication with a I send and I receive operation, which then essentially gives you the operation of saying, I want to have all my neighbors informed about this. Here's, let's say, the decomposition of 4. You can also think about including the diagonal neighbors. But basically here we have this simple setup. And then, of course, with the I receive in the end, the other view, how you would actually compute this. And at some point in time, you may be interested to have this wait all for all of these message exchanges to be ready. And then you maybe can say how much you received and done. But normally you would now have a for loop of doing this many different times, right? The whole application. So this is just a loop of saying, I do this 4 times because I have 4 neighbors defined. But of course, then after this, normally would have an application example where then also then the Cartesian maybe kicks in, because you here and there will also have the reach of the neighbors here. So essentially, in order to get to the neighbors on the other side, you basically have to use a Cartesian communicator here with shifts and so forth. But this is something what we also will see in HPC climate simulation that will yourself be a little bit experimenting with in later lectures. Just show you that really non-blocking communication is, of course, used. And one really complex application example we will look at is numerical weather prediction in this MPI codes. But they are really in lecture 15 towards the end of the course, when we know much more substance about many different aspects of how we solve and deal with ordinary and partial differential equations, why they matters, how they basically are used for physics, for fluid flow, motion, etc. And this will be an advanced application example, just alluding to the point that, of course, from simple arrays I showed and started in the first part here now, of course, this will be much more an order of magnitude of scale, essentially thinking about the whole Earth, but also regional weather forecasts and so forth, where NWP is basically the technique of choice. So the final aspects, also alluding a little bit to the idea of using libraries, of thinking already that I/O is important, is something where we then think about in this particular example of climate. We have lots of data to be computed. And what we learned in lecture 4 in the second half was really it's not only about compute, right? It's also about the data. A little bit explained here. You see this compute processes using parallel to a parallel file system, where basically different options exist also that do not scale. If you have here, let's say some node determined to just write the data, or basically have different IO processes that you cut it down. This is basically something where you have to be a little bit, careful what pattern you really employ. And we learned already that parallel is really important and has some tricks that we also learned then in lecture 15, where basically many of these aspects maybe also are very costly in terms of writing every time. And usually what you want to do is here and there using essentially certain standards for data, like parallel net CDF is in the earth science community quite established for storing the data in parallel, basically in order to really have this in parallel written to one file, which is a net CDF file and so forth. More of this will come later. And again, there will be other examples of interesting application examples like lecture 13, where we think about a complete different idea of more stochastic methods with Monte Carlo simulations, here in protein folding simulations, which are basically considering and targeting diseases like Alzheimer's if the protein is folded wrongly, and give hints to this. And these are all application examples we will talk in later lectures, just showing you already examples, so to speak, as an appetizer, that at the end of the course, we will go into some more elaborate MPI examples. But we are still, in a way, learning the basics of MPI. And here you see also application examples, more of this N-body simulations already started with the astrophysics simulations. Of course, here we have a different force, between particles that you here want to compute. It's actually a hydrodynamic fluid simulation, but and based on gas and so on. And also this will be given in much more detail in lecture 14. So interesting parts will come in the, let's say, second half of this course, where we of course go more into applications. Here's also another nice example where people in finite element simulations and then related to computational fluid dynamics have many different applications. Here you see basically a car crash simulation that I brought to you as a video, and basically have a look at this short video to understand why HPC can be useful also for real life problems. Okay, that was, of course, just a short, simple example. We will elaborate on this, of course, in the CFD and finite element lecture much more in detail. One of my PhD students will really give you their hands-on lecture, being part of the simulation data lab fluid dynamics here in Iceland. So very an expert in the field. And we stop here with part 1, and we'll continue after that a bit more with a view on data and data structures in the second part of this lecture.